Welcome back. In the previous video, we have seen how to calculate the noise voltage of open terminated resistor, and this resistor has a temperature T. And we said that the noise voltage, it can be approximated as the square root of 4kTB multiplied by R, where K is Boltzmann constant, T is the temperature in Kelvin, absolute temperature in Kelvin, B is the bandwidth in Hertz, and R is the resistance in Ohm. This is actually the noise voltage, but we are not concerned with the noise voltage. We are concerned about the noise power, because the receiver is talking about the received signal, the received power signal, or the power of the received signal. So we are talking about the noise power. So what is the delivered noise by this resistor to the system? Effectively, to obtain the maximum output power from a specific source, it should be matched to the load. So assuming that we are going to connect this noisy resistor to an ideal load with the same impedance, so the impedance here of the load, it would be exactly the same as the required resistance R, and this connected through an ideal band pass filter with the operating bandwidth B, such that only the power in the required bandwidth will be transferred from the noisy resistor to the load resistance. In this case, we can say that, okay, the maximum power transfer to the load resistance, it would be the value of Vn squared over 2R squared. So it would be simply Vn over 2R, all of them squared. This is the maximum current. This is the maximum current I squared multiplied by the resistance R. So the maximum power transferred from the noisy resistor to the load resistor, it would be V noise over 2R squared, which corresponds to the current I squared, multiplied by the resistance R. By simplifying this, it would be Vn squared over 4R. So Vn squared, and here we have 4R squared in the denominator, and we have R here. So it would be Vn squared over 4R. And by replacing Vn by square root 4kTBR, so Vn squared will be 4kTBR over 4R. This means that the maximum noise power delivered from the noisy resistor to the load resistance, it would be K multiplied by T multiplied by B. Or in other words, the maximum power transfer from the noisy resistor with the result that the power delivered to the load and in a bandwidth B would be KTB. It is interesting to note that this power, this maximum power, does not depend on the value of R. It depends on Boltzmann constant, the temperature of the resistance, and the operating bandwidth of the system. So note that this noise power is independent of the frequency, is independent of the value of the resistance. Such noise source has power spectral density that is constant with frequency. So at any frequency band, it would have the same value. So it depends on the bandwidth, not the frequency. And is an example of a white noise source. So the noise power from a resistor due to thermal noise is KTB. K, Boltzmann constant, T is the temperature, B is the operating bandwidth. Also, it can be noted that the noise power is directly proportional to the bandwidth, which in practice is usually limited by the passband of the RF or microwave system. Independent white noise sources can be treated as Gaussian distributed random variables. So the total noise from different white source noise would be simply the addition of these white noises. So the noise power or variance of the independent noise source are additive. So the total noise would be simply the additive noise. According to what we have found, that the noise power is KTB, it means that if the bandwidth is tending to zero, if I reduce the operating bandwidth, the noise power would be is tending to zero. So the system with smaller bandwidth will collect less noise power. For example, if I'm talking about the spectrum analyzer, the noise floor of the spectrum analyzer depending on the operating bandwidth of the spectrum analyzer. So by reducing the bandwidth, we will find that the noise floor of the spectrum analyzer will be reduced. If I reduce the bandwidth 10 times, the noise floor will be reduced 10 dB, and so on. On the other hand, as the temperature tends to zero, the noise power will tend to zero. This means that the cooler device and components will generate less noise power. This is actually the reason why low noise amplifiers usually are used in liquid nitrogen, for example, to cool the low noise amplifier, to reduce the noise figure of this amplifier, or the noise temperature of this amplifier. On the other hand, if the bandwidth is increasing to infinity, the noise power will be increasing to infinity, and this is actually non-practical case, and this is known as ultraviolet Kasparov effect. So if the bandwidth of the system is increasing to infinity, the noise would be increasing to infinity, and this is actually not a practical case, because almost every receiver system or every microwave system has specific operating bandwidth, which does not occur in reality. Okay, all right. So now we define the noise power due to a resistor in terms of the temperature of this resistor. The question now, if I'm not talking about a resistor, I'm talking about, for example, a microwave receiver, microwave system. So this microwave system with arbiter white noise source, I don't know what is inside the circuit, maybe resistor, maybe transistor, anything here, and it is connected to a certain load. So some power or some noise power will be delivered from this arbiter white noise source to the load. And assuming that this is the maximum power which can be delivered from this noise source to the load, so this is actually equivalent. I can replace this arbiter white noise source by an equivalent resistance equal the load resistance R to transfer the maximum power, and this resistance at an effective temperature, not a physical temperature, an effective temperature, and this effective temperature with this resistance will introduce the noise power in the node here at the load resistance. And as we said, the noise power or the output noise is K multiplied by T multiplied by B. So in this case, the effective temperature would equal the value of the noise delivered to the load resistance over the value of K multiplied by the operating bandwidth. This is the effective temperature for the hypothetical resistance inside this arbiter white noise source. This means that any noise source, it can be replaced by an equivalent resistance such that the value of this resistance equal the load resistance, and the equivalent temperature of this resistance correspond to the value KTE multiplied by B equals the value of the noise delivered to the load resistance. That's what we are seeing here. If an arbitrary source of noise, thermal or non-thermal, but it is a white noise, the main condition is a white noise. So the noise bar is not strong function of frequency, it is flat with frequency over the bandwidth of interest. This arbitrary white noise, it can be modeled as an equivalent thermal noise source or equivalent resistor, and characterized by equivalent noise temperature TE. So the equivalent thermal noise source is a resistor with the same value of the load resistance. Why with the same value of the same resistor? To introduce maximum power transfer from the noise source to the load resistor. And the value equivalent noise temperature, it would be as the value of K TE multiplied by B equals the value of this noise value. Or in other words, the value of TE, the equivalent or effective noise temperature, is the value of the noise over Kp. By using this in a simple amplifier, assume that we have a noisy amplifier and this amplifier is terminated at its input and its output by ideal matched loads. Ideal matched loads, which means that it does not include any noise. So we are here matched load with a resistance R at the input and matched load at the output R at the output. And we have internal noise here. So the input noise from the input port is actually zero. But the internal noise inside the amplifier will introduce output noise in output here. And the value of in output here is terminated by the resistance or the matched resistance R. So we can replace all this system by a resistor with a noise temperature. So in this case, the effective temperature TE, it would be simply the value of noise over K multiplied by B. Now I have replaced all this system. What will be the situation if I have introduced this noise source at the input of the amplifier? So effectively the amplifier is amplifying the input signal by a gain G. So in this case, we are going to introduce input noise Ni, which when will be amplified by G, it will equal the output noise. So the output noise, it would be G multiplied by K, the equivalent temperature TE multiplied by B. K multiplied by TE multiplied by B is effectively the noise coming from this resistor. The noise coming from this resistor. So the effective temperature here, it would be the output noise over G K multiplied by B. The effective temperature here would be the output noise over G, the gain, multiplied by K multiplied by B. So the input noise here, in this case, it would be K multiplied by T effective or T equivalent multiplied by the bandwidth. If we are going to multiply this, so it would be K multiplied by N naught over G over K over B multiplied by B. B will be eliminated with B. K will be eliminated with K. So we have noise output over G. Noise output over G will be amplified by G. So the output here would be noise output. This means that the noisy amplifier, it can be replaced by noiseless amplifier with an input resistor which has an effective temperature equal the output noise of the noisy amplifier over the gain of the amplifier multiplied by Kb. Okay? This is the equivalent noise temperature for a noisy amplifier. Usually, when we are going to measure the noise, we use calibrated noise sources. So it is sometimes useful for measurement purposes to have calibrated noise sources. As an example for calibrated noise sources, we have passive noise sources, which is maybe simply consists of a resistor or matched load, but this resistor is held at a constant temperature. So the temperature of this resistor is constant, such that the noise value, it would be K multiplied by the physical temperature T multiplied by the operating bandwidth. This constant temperature can be obtained by a temperature controlled oven or cryogenic flask, for example. Another example for noise sources is active noise source. Active noise sources, it can be diode or transistors or tube, which provide calibrated noise output power. And effectively, in the case of active noise sources, the value of the noise is much greater than the conventional or the thermal noise of a simple resistor at the ambient temperature. So, noise generators, especially active noise sources, can be characterized by the equivalent noise temperature. But more common measurement is noise power for such component is the exist noise ratio. Effectively, the exist noise ratio is defined as if I have a noise generator introducing noise Ng, while the ambient noise due to the ambient temperature or the room temperature is N naught. So the exist of noise ratio in dB is 10 log the value of the generated noise minus the ambient noise over the ambient noise. And because the noise is represented in equivalent temperature, so we can say that simply 10 log the effective temperature for the noise generator minus the ambient temperature T naught over the ambient temperature, where Ng and Tg here are the noise power and the equivalent noise temperature of the noise generator. N naught and T naught are the noise power of the temperature associated with the room temperature or the ambient noise. And room temperature is usually around 290 kelvins for passive source of matched load. Usually, solid state noise generator are characterized in terms of the exist noise ratio, not the effective temperature. So solid state noise generator typically have exist noise ratio in the range from 20 to 40 dB. These are some types of the noise sources which are mainly used in noise measurements. In the following video, we are going to talk about what are the measurement techniques for noise temperature. So assume that I have an amplifier. How can to determine the noise temperature of this amplifier? That's what we are going to see in the following video. Okay.